I'm Mr. Joseph, your chemistry teacher. I'm back with my lectures, still on states of matter. So we consider the gaseous state. Our lesson objectives for today. At the end of the lesson, students should be able to state the basic assumption of the kinetic theory as applied to an ideal gas. That is the kinetic theory of gases. So they should be able to state the basic assumptions of the kinetic theory of what? An ideal gas. Also explain qualitatively in terms of intermolecular forces and molecular size. Then look at the conditions necessary for a gas to approach ideal behavior. Then the limitations of ideality at very high pressures and very low temperatures. So please, I want us to listen attentively and get the best from today's lecture. So still on states of matter, we're looking at the gaseous state. Now, based on the kinetic theory of matter, it states that what matter consists of tiny particles, and these particles are in what? Constant random motion. The idea that molecules in gases are in constant movement is called the kinetic theory of gases. This theory makes certain assumptions, of which we are going to consider that gas molecules move rapidly and randomly. Yes, gases consist of what? Particles, and these particles are in constant random motion. So the gas molecules move rapidly and randomly. Then the next is what? The distance between the gas molecules is much greater than the diameter of the molecules, so the volume of the molecules is negligible. That means particles in the gas have no volume and are very what? Far apart. That is, the volume of gases are negligible. That is, particles in the gas have no volume and are very what? Far apart. Then the next is particles in a gas do not attract or repel one another. There are no intermolecular force of attraction or repulsion between what? Gas molecules. That's what the kinetic theory is trying to explain, that particles in a gas do not attract or repel one another. There are no intermolecular force of attraction. Then the next is all collisions between particles are elastic. This means no kinetic energy is lost in collision. Kinetic energy is the energy associated with moving what? Particles. Then the next is the average kinetic energy of all the gas particles in a sample is proportional to the temperature of the gas sample. That means as the temperature increases, the kinetic energy will increase. That is, the average kinetic energy of all the gas particles in a sample is proportional to what? To the temperature of that gas sample. So any gas that obeys the kinetic theory of gases, any gas that obeys the kinetic theory of gases completely is what we call what? An ideal gas. And in reality, there is no what? Ideal gas, because real gases doesn't completely obey the kinetic theory of gases, which are the basic assumptions of the kinetic theory of gases. I want us to pay attention and get the best as we proceed. Having considered the kinetic theory of gases, based on the basic assumptions of the kinetic theory of gases, it states that what? There are no intermolecular force of attraction or repulsion between gas molecules. That means gas molecules doesn't have intermolecular force of attraction, but in reality, real gases, they have intermolecular force of attraction, such as van der Waals force, permanent dipole force, hydrogen bond. But based on the kinetic theory of gases, there are no intermolecular force of attraction or repulsion between gas molecules. And it also states that when the volume of gases are negligible small compared to the volume of the container, that means there is no volume. There is no volume. But in reality, gas molecules, they have volume. But based on the kinetic theory of gases, the volume of gases are negligible small compared to the volume of the container. What it's trying to tell us is that the volume of gases are what? Insignificant. So that brings us to what we call the ideal gas. Any gas that obeys the kinetic theory of gases completely is called what? An ideal gas. A theoretical gas that fits this description is called an ideal gas. In reality, the gases we encounter don't fit this description exactly, although they may come very close. The gases we encounter are what? Real gases. In real gases, such as ammonia, chlorine, hydrogen, nitrogen, there are intermolecular forces of attraction or repulsion between the molecules. And the volume of these gases are not negligible. The volume are very, very significant. So real gases do not always obey the kinetic theory in two ways. There is not zero attraction between the molecules. Yeah, there is no zero attraction. There are intermolecular forces of attraction between the molecules. And we cannot ignore the volume of the molecules themselves. Yeah, the volume of the molecules cannot be ignored. So noble gases with small atoms such as helium and neon with weak intermolecular forces such as van der Waals force of attraction approach ideal gas. So gases with weak intermolecular force of attraction, they tend to behave like what? Ideal gases, because in an ideal gas, there are no intermolecular force of attraction or repulsion between the gas molecules. So small atoms with what? Weak intermolecular force of attraction, like van der Waals forces, gases with small atoms and weak intermolecular force of attraction, they tend to behave like what? Ideal gas. They approach ideal behavior. This is because the intermolecular forces are small, while gases with strong intermolecular forces like ammonia, they have hydrogen bond, steam with hydrogen bond, and other what? and other gases with strong intermolecular force of attraction, they deviate from what ideal gas. So the stronger the intermolecular force of attraction, the deviation from an ideal gas, because in an ideal gas, there are no intermolecular force of attraction or repulsion between the gas molecules. So gases with weak intermolecular force, they tend towards ideal gas. They approach ideal gas behavior compared to gases with strong intermolecular forces of attraction. So in reality, there is no ideal gas. Any gas that fit into the description is what we call an ideal gas. But real gases, they deviate from ideal gas. There are in real gases, there are intermolecular force of attraction and repulsion. The volume of the gases are significant. So that is as simple as ABC. So having considered ideal gas and real gases, in an ideal gas, there are no intermolecular force of attraction or repulsion between the gas molecules. In an ideal gas, the volume of the gases are negligible small compared to the volume of the container. That means in an ideal gas, there is no volume. But in real gases, there are intermolecular forces of attraction such as van der Waals forces, permanent dipole force, and hydrogen bond. In real gases, they have volume. The volume of the gases are significant. So we want to consider under what condition of temperature and pressure that real gas differ or deviate from ideal gas. So real gases deviate or differ from ideal gases at low temperature and high pressure. Now what happened at high pressure? What happened is that the volume of the particles take up a larger proportion of the volume occupied by the gas. So what happened is that the volume becomes very, very significant at high pressure. Ideal gas assume that they occupy negligible volume, but at a high pressure, the volume of the particles take up a larger proportion of the volume occupied by the gas. And at high pressure, intermolecular forces are also greater as the particles get closer together, because at a high pressure, the gas molecules collide with themselves and also with the walls of the container. So they get closer. So the intermolecular force becomes significant. So at high pressure, real gas differ or deviate from an ideal gas. Then at low temperature, what happens is that at low temperature, the particles have little energy and so can be pulled together by attractive forces. So the intermolecular force of attraction becomes significant. But ideal gas assume that the attractive forces are negligible. But at low temperature, the attractive forces become more significant and no more negligible. So real gases differ or deviate from ideal gas at low temperature and high pressure. That means if real gases differ or deviate from ideal gases at low temperature and high pressure, that means real gases behave like an ideal gas at high temperature and low pressure. That means real gases will tend to approach ideal gas at high temperature and low pressure, because the reverse will be the case at high temperatures and low pressure. It's as simple as ABC. So we want to consider the ideal gas laws. So we're starting with Boyle's law. Boyle's law states that the volume of a given mass of gas is inversely proportional to its pressure at constant temperature. That means as the volume increases, the pressure decreases. So at constant temperature, the pressure and volume are inversely related. In other words, as volume decreases, the pressure increases and vice versa. So mathematically, that means the volume is inversely proportional to 1 over P, which is the pressure at at constant temperature. At constant temperature. So the volume is inversely proportional to its pressure. So if we remove this variation sign, we'll have V is equal to K bracket 1 over P, where K is equal to constant. So if we make K the subject of the formula, that means V will be equal to K over P. Therefore, K now will be equal to PV. So if we are to consider the initial pressure and the final pressure and the initial volume and the final volume, that means we'll have K1, which is a constant, is equal to P1 V1, and K2 will be equal to P2 V2, where P1 is the initial pressure, V1 is the initial volume, P2 is the final pressure, V2 is the final volume. Since K1 is a constant and K2 is a constant, so K1 will be equal to K2, because constant is equal to constant. If K1 is equal to K2, that means we'll have P1 V1 will be equal to P2 V2. So this is the mathematical representation of Boyle's law. P1 V1 is equal to P2 V2. So if we are given P1 V1 P2, we can calculate V2. So the volume of a given mass of gas is inversely proportional to its pressure at constant temperature. So it's as simple as ABC. So this is the mathematical representation of Boyle's law. This is the graphical representation. Volume is inversely proportional to pressure. As volume As volume increase, pressure what? Pressure decreases. As volume increase, the pressure decreases. So this is the graphical representation of the Boyle's law, and this is a graphical representation of the Boyle's law. Volume is inversely proportional to its what? To its pressure. I think I need to erase this so that you see it very, very well. This is a graphical representation of Boyle's law, that the volume is inversely proportional to its pressure at constant temperature. So this is a graphical representation. Any of these can represent what? Can represent the Boyle's law graphically. So it's as simple as ABC. So still an ideal gas law. So we want to consider the Charles law. The Charles law states as well, the volume of a given mass of gas is directly proportional to its temperature at constant pressure. As far as the pressure remains constant, the volume is directly proportional to temperature based on Charles law. So the volume of a gas is directly proportional to the Kelvin temperature if the pressure is held constant. So as the temperature increases, the volume also increases in a linear relationship. So mathematically, that means volume is directly proportional to what? Temperature at what? At constant pressure. At constant pressure. So if we remove the variation sign, that means V will be equal to what? KT, where K is the constant. So make K the subject to the formula. K now will be equal to what? V over what? Over T. So considering, the initial volume and the initial temperature of gases and the final volume and the final temperature of the gases, that means we'll have K1 will be equal to what? V1 over T1, and what? K2 will be equal to what? V2 over what? T2. So since K1 is a constant and K2 is a constant, that means we'll have K1 is equal to what? K2. Constant is equal to constant. So if K1 is equal to K2, that means V1 over T1 will be equal to what? V2 over what? Over T2. So this is the graphical representation of what? This is the mathematical representation of Charles law. V1 over T1 will be equal to what? V2 over what? Over T2. That means the volume of a given mass of gas is directly proportional to its temperature at constant what? Pressure. So this is the mathematical representation. This is the graphical representation of Charles law, and this is the mathematical representation. So let me erase these two so you see the graphical representation of Charles law. Where volume is directly proportional to its temperature at constant pressure. So as the volume increases, the temperature increases. As the temperature increases, the volume increases. As the temperature decreases, the volume what? Decreases also. So this is a graph of what? Volume. This is a graph of volume against what? Against temperature in Kelvin. This is a graph of volume against temperature in degrees Celsius. So any of this graph can represent what? The ID gas law, which is what? Charles law. That the volume of a given mass of gas is directly proportional to its Kelvin temperature if the pressure is held constant. So it's as simple as what? A, B, C. So still on ideal gas laws, we are looking at the Avogadro's law, which states that equal volume of all gases at the same temperature and pressure contain the same number of moles. So Avogadro's law states that the volume of a sample of gas is directly proportional to the number of moles in the sample at constant temperature and pressure. So we have to do with we have to do with constant temperature and pressure. As far as the temperature and pressure remains constant, that means the volume of a given mass of gas, is directly proportional to the what? Number of moles. So if we remove this sign, we'll have V will be equal to what? K N. N where K is a constant. So if we make K the subject, K now will be equal to what? V over what? Over N. So considering K being a constant, if we look at the initial volume and the final volume of gases, initial moles and the final number of moles of the gases, we'll have K1 will be equal to what? V1 over what? N1, and K2 will be equal to what? V2 over what? N2. So if K1 is equal to K2, since both of them are constant, K1 is equal to what? K2. That means V1 over what? N1 will be equal to what? V2 over what? Over N2. So at constant temperature and pressure, the volume of what? The volume of a given mass of gas is directly proportional to the number of moles in the sample, as far as the temperature and pressure remains what? Constant. So which is the Avogadro's law. If the amount of gas in the container is increased, the volume is increased. If the amount of gas in the container is decreased, the volume is decreased. So graphically, we have what? We have a graph of what? Volume against what? Number of moles. So that means the volume is directly proportional to the number of moles. As the volume increases, the number of moles will increase. So these are the ideal gas, the Boyle's law, the Charles law, the Avogadro's law. We have volume relates temperature, when volume relates pressure, and when volume relates number of moles. So it's as simple as what? A, B, C. So I want to look at the derivation of the ideal gas equation, which is a combination of Boyle's law, the Charles law, and the Avogadro's law. So if we combine the Boyle's law, we state that the volume of a given mass of gas is inversely proportional to its pressure. Combine the Boyle's law plus the Charles law. The Charles law, which states as what the volume of a given mass of gas is directly proportional to its temperature at constant pressure, plus the Avogadro's law, which states that equal volume of all gases at the same temperature and pressure contain the same number of moles. So for the Boyle's law, V is inversely proportional to its pressure. For the Charles law, V is directly proportional to temperature. For the Avogadro's law, V is directly proportional to what? The number of moles. Now, if you look at the three gas laws, what is common among them is the volume. So if we combine the Boyle's law, Charles law, and Avogadro's law, we have an equation. Volume is directly proportional to what? Temperature, and also directly proportional to number of moles, and inversely proportional to its pressure. So we'll get this. So this is a combination of Boyle's law, Charles law, and Avogadro's law. From this, the volume is directly proportional to the temperature and the number of moles, and inversely proportional to what? Pressure. So if we remove the variation sign, we establish a constant known as the gas constant. That means V will be equal to what? N what? RT over what? Over P. Here R is equal to what? A constant. R is a constant known as what? The gas constant. Known as gas constant. Gas constant. Gas constant. R is a gas constant. So if we cross multiply, make PV the secondary formula, we now have what? PV is equal to what? nRT. So we did the ideal gas equation. So arrive at the what ideal gas equation. With the help of this equation, we can calculate the pressure if we are given the volume, the number of moles, and the temperature. R is a constant. We can calculate the volume if we are given the pressure, given the number of moles, and the temperature. R is a constant. You can calculate the number of moles if you are given the pressure, the volume, and the temperature. You can calculate the temperature if you are given the pressure, the volume, and the number of moles. R is always what? A gas constant. So there are other factors we can also calculate. We can calculate the mass of the gas. We can calculate the molar mass of the gas. We can also calculate the density of the gas. So I have to erase this. Let me derive on how you can calculate other values from the ideal gas equation. Now, having established the ideal gas equation, which is PV is equal to what? nRT. We remember that the number of moles of gas, which is N, number of moles of gas is equal to mass over what? Molar mass. So if I were to substitute into the ideal gas equation, that means PV is equal to what? Mass over what? Molar mass of the gas multiplied by the gas constant and what? And temperature. So from this, we can calculate the mass of the gas. All we just need to do is make the mass of the gas the subject to the formula. So if we make M the subject to the formula, mass now will be equal to what? Mass now will be equal to what? PVMR over what? RT. So we can calculate the mass of the gas. So we'll have what? The volume, we'll have the pressure, we'll have the molar mass, we'll have the gas constant, and the what? And the temperature. We can also calculate what? We can also calculate the molar mass of the gas. So molar mass of the gas. To calculate the molar mass of the gas, make the molar mass the subject to the formula. Molar mass now will be equal to what? MRT over what? Over PV. So with this, we can calculate the molar mass of the gas. You have the mass, you have the gas constant, you have the temperature, you have the pressure, and you have the what? And you have the volume. So we can calculate the molar mass of the gas. Another value we can calculate is the density of the gas. So what we need to do is to what? You know that I have to erase this so that I will have enough space. You know that density is equal to what? Mass over volume. Density is equal to mass over volume. Now what happened? The formula to calculate molar mass is mR is equal to what? mRT over what? Over PV. Now density is equal to mass over volume. So this is mass over the volume. If we substitute density here in place of mass over volume, then the molar mass now will be equal to what? Density times what? The gas constant times what? Temperature over what? Over the pressure. So when you erase this, let me erase this so that I'll have enough space. I have to erase this. So that I'll have enough space. Enough space to solve. So molar mass is equal to density times the gas constant times temperature over the pressure. So we have to make density the subject to the formula, make D the subject to the formula. That means density now will be equal to what? Pressure times the molar mass divided by what? Gas constant and what? And temperature. So D is the density of the gas. So we can calculate the density what? Density of the gas, which is the pressure of the gas times the relative molecular mass of the gas divided by the gas constant and the what? And the temperature. So it's as simple as what? A, B, C. So with the ideal gas equation, we can calculate the mass of the gas, we can calculate the molar mass of the gas, we can calculate the density of the gas, we can calculate the temperature of the gas, we can calculate the volume of the gas, we can calculate the pressure of the gas, we can calculate the number of moles of the gas. So it's as simple as what? A, B, C. So from the above derivation of the ideal gas equation, you can see that the ideal gas law is the equation of the state of a hypothetical gas, which is what PV is equals to nRT, where P is the pressure of the ideal gas. Pressure can be in Pascal, it can be in Newton per meter square, it can be in atmosphere, it can also be in millimeter mercury height. V is the volume of the gas, which can be in meter cube, it can be in cm cube, it can be in dm cube. N is the amount of ideal gas measured in terms of mole. N is just the number of moles. R is the universal gas constant, which is in joule per mole per Kelvin, and T is the temperature of the gas, which can be in degrees Celsius or in what? In Kelvin. So it's as simple as what? ABC, which is the ideal gas equation. From the ideal gas equation, PV is equal to nRT. You can calculate the pressure of the gas, the volume of the gas, the number of moles of the gas. You can go as far as calculating the mass of the gas, the molar mass of the gas, the density of the gas. So it's as simple as what? ABC. Now, having discussed ideal gas and real gases, the real gases, they have intermolecular force of attraction or repulsion, and the volume of the real gases are not negligible, small compared to the volume of the content. That means real gases have volume, which is a deviation from the ideal gas, where there are no intermolecular forces of attraction or repulsion between the gas molecules, where the volume of the gas are negligible, small compared to the volume of what? The container, which is they don't have volume. Now, if you look at a graph, if you look at the graph before us, it's a graph that tends to explain what the ideal gas and the real gas and the deviation from the ideal gas and the real gas. In an ideal gas, PV is a constant, and a plot of PV against P would be expected to give a horizontal line, which is what? Indicating what? The ideal gas. The horizontal line, which indicates what? The ideal gas. Ideal gas. So other gases are what? The real gases. They deviate from ideal gas, like methane, like carbon monoxide, like hydrogen, and what? Helium. All these gases, they deviate from an ideal gas. So this is a graphical representation of the real gases and ideal gas. So the horizontal line shows the what? The ideal gas. You can see ideal gas volume is 22.4 dnq per mole at 0 degrees Celsius. So this is a graphical representation of what? Real gases and what? Ideal gas. So the straight line horizontal straight line indicate an ideal what? An ideal gas. So this shows the deviation of rare gases from what? From an ideal gas. So as you can see, this is also a graphical representation of rare gases and ideal gases. So you can see the deviation of rare gas from what? Ideal gas. Nitrogen is a rare gas, carbon dioxide is a rare gas, and other examples which are what? Rare gases. So these are graphical representation to differentiate what the rare gases from what? Ideal gases. Now deviation from an ideal gas becomes greater at high pressure and low temperature. Yes, rare gases, they deviate from ideal gas at what? At high pressure and low temperature. So you can see, so this is the ideal what? This is the ideal gas. The straight line indicating what? This is the ideal gas. So this is the ideal gas. While this is nitrogen, which is the real gas. Deviate from what? Ideal gas. From an ideal gas. The straight line is an indication of what? That the gas is an what? Ideal gas. It's an ideal gas. So all these ones are real gases. Nitrogen is a real gas. You can see the deviation from the ideal gas. Carbon monoxide is also what? A real gas. So this is graphical representation of what? An ideal gas and also what? Real gases. So it's as simple as what? A, B, C. Just feel free to reach out to me if you encounter any difficulty. I'm always there for you. I'm Mr. Joseph, your chemistry teacher. So please don't forget to subscribe to my YouTube channel, like, share, and reach out to me if you encounter what? Any difficulty. I'm always there for you. Thank you very much for listening. So before us, a typical chemistry A-level question on ideal gas equation. So the general gas equation can be used to calculate the value of the molar mass of a gas. For a sample of a gas of mass m grams, which expression will give the value of mr, which is the molar mass of the gas. So having considered the ideal gas equation, so we'll have PV is equal to what? nRT, and you know that N is equal to what? The mass over what? Molar mass. That means what? PV will be equal to what? Mass over molar mass RT. So all we just need to do to make molar mass the subject of the formula, if we cross multiply, therefore to make molar mass the subject of the formula, molar mass MR will be equal to what? MRT over what? PV. So that will be the molar mass. MRT over what? PV. So the correct answer to this question is what? A. A is the correct answer, which is MRT divided by what? Pressure times the volume of the gas. So it's as simple as what? A, B, C. So these are typical A-level exam question on ideal gas equation. It's as simple as A, B, C. Thank you very much. Attempt as many questions as possible and feel free to reach out to me if you encounter any challenge or any difficulty. I'm always there for you. So this is a typical chemistry A-level question on ideal gas. Which substance shows the greatest deviation from the properties of an ideal gas under room conditions? In an ideal gas, there are no intermolecular forces of attraction or repulsion, but in real gases, there are intermolecular forces of attraction or repulsion. Now, the real gas that has the strongest intermolecular force of attraction shows the greatest deviation from an ideal gas, while the one that have the lowest intermolecular force of attraction, that is the one that tend to behave like what? An ideal gas, or they tend towards what? Ideal gas. And we'll have the van der Waals force, which are the weakest intermolecular force of attraction. We'll have the permanent dipole force, and we'll have what? The hydrogen bond. So the gas that has hydrogen bond, which is the strongest intermolecular force of attraction, is the gas that shows the greatest deviation from an ideal gas. So the correct answer to this question is what? D. Correct answer to this question is D. Is D, which is what? Ammonia, that have what? Hydrogen gas, which is the strongest intermolecular force of attraction, shows the greatest deviation from an ideal gas. Other gases, they have what? Weak intermolecular force of attraction, which are van der Waals force. So ammonia shows the greatest deviation from an ideal gas. So it's as simple as ABC. Attempt as many questions as possible and feel free to reach out to me if you encounter any challenge or any difficulty. I'm always there for you. I'm Mr. Joseph, your chemistry teacher. So before us, a typical A-level chemistry question, typical examination question on ideal gases and non-ideal gases. So the PV, The value of PV is plotted against P for two gases, an ideal gas and a non-ideal gas, where P is the pressure and V is the volume of the gas. So this is the graphical representation. You are now asked which of the following gases shows the greatest deviation from what? Ideality. So please attempt this question. It's as simple as ABC. Go through the slides, attempt the question. If you encounter any difficulty, feel free to reach out to me. I'm always there for you. It's a typical examination question. So please go through it and reach out to me if you encounter any challenge or any difficulty. So this is a typical examination question, chemistry A-level question that has to do with ideal gas and non-ideal gas. For an ideal gas, the plot of PV against P is a straight line. For a real gas, such a plot shows a deviation from ideal behavior. The plots of PV against P for three gases are shown below. The gases represented are ammonia, hydrogen, and nitrogen, which are real gases. What are the identities of the gases X, Y, and Z? So attempt this question. It's as simple as ABC, and feel free to reach out to me if you encounter any challenge or any difficulty. So go through the slide and attempt this question. This is a typical examination question. Feel free to reach out to me if you encounter any challenge or any difficulty. I'm always there for you. I'm Mr. Joseph, your chemistry teacher. Feel free to reach out to me. And please don't forget to subscribe to my YouTube channel, like, share, and reach out to me if you encounter any challenge or any difficulty. Or if you need any help, feel free to reach out to me. I'm always there for you. I'm Mr. Joseph, your chemistry teacher. Thank you very much. Subscribe to my YouTube channel, comment, like, share, and reach out to me if you encounter any challenge or any difficulty. I'm always there for you. I'm Mr. Joe, your chemistry teacher. Subscribe to my YouTube channel. Thank you very much. Mr. Joe, your chemistry teacher.